2.1 Mountain Building, Convergent Boundaries, and Plate Tectonics. Mountains are often spectacular features that rise abruptly above the surrounding terrain. Some occur as isolated masses. The volcanic cone Kilimanjaro, for example, stands almost 6,000 meters, or 20,000 feet, above sea level, overlooking the expansive grasslands of East Africa. Other peaks are part of extensive mountain belts, such as the American Cordillera, which runs almost continuously from the tip of South America through Alaska. Chains such as the Himalayas consist of youthful, towering peaks that are still rising, whereas others, including the Appalachian Mountains in the eastern United States, are much older and have eroded far below their original lofty heights. Most major mountain belts show evidence of enormous horizontal forces that have folded, faulted, and generally deformed large sections of Earth's crust. Although folded and faulted strata contribute to the majestic appearance of mountains, much of the credit for their beauty must be given to weathering and mass wasting processes, and to the erosional work of running water and glacial ice, which sculpt these uplifted masses in an unending effort to lower them to sea level. Mountain building has occurred during the recent geologic past in several locations around the world. Young mountain belts include the American Cordillera, which runs along the western margin of the Americas, from Cape Horn to Alaska, and includes the Andes and Rocky Mountains. Also, the Alpine Himalayan chain that extends from the Mediterranean through Iran to northern India and into Indochina. And the mountainous terrains of the western Pacific, which include volcanic island arcs such as Japan, the Philippines, and Sumatra. Most of these young mountain belts have come into existence within the last 100 million years. Some, including the Himalayas, began their growth as recently as 45 million years ago. In addition to these young mountain belts, several chains of Paleozoic and Precambrian age mountains exist on Earth as well. Although these older structures are deeply eroded and topographically less prominent, they clearly possess the same structural features found in younger mountains. The Appalachians in the eastern United States and the Urals in Russia are classic examples of this older group of mountain belts. Over the last few decades, geologists have learned a great deal about the tectonic processes that generate mountains. The term for the processes that collectively produce a mountain belt is orogenesis, derived from oros, meaning mountain, and genesis, meaning to come into being. Some mountain belts, including the Andes, are constructed predominantly of lavas and volcanic debris that erupted on the surface, as well as massive amounts of intrusive igneous rocks that have solidified at depth. However, most major mountain belts display striking visual evidence of great tectonic forces that have shortened and thickened the crust. These compressional mountains tend to contain large quantities of pre-existing sedimentary rocks and crystal and crustal fragments that have been contorted into a series of folds. Although folding and thrust faulting are often the most conspicuous signs of orogenesis, metamorphism and igneous activity are always present in varying degrees. Over the years, several hypotheses have been put forward regarding the formation of Earth's major mountain belts. One early proposal suggested that mountains are simply wrinkles in Earth's crust, produced as the planet cooled from its original semi-molten state. As Earth lost heat, it contracted and shrank. In response to this process, the crust was deformed, similar to how the peel of an orange wrinkles as the fruit dries out. However, neither this nor any other early hypothesis was able to withstand careful scrutiny. With the development of the theory of plate tectonics, a model for orogenesis with excellent explanatory power has emerged. According to this model, most mountain building occurs at convergent plate boundaries. Here, the subduction of oceanic lithosphere triggers partial melting of mantle rock, providing a source of magma that intrudes the crustal rocks that form the margin of the overlying plate. In addition, colliding plates provide the tectonic and metamorphose the thick accumulations of sediment that have been deposited along the flanks of land masses. Together, these processes thicken and shorten the continental crust, thereby elevating rocks that may have been formed near the ocean floor to lofty heights.